Hey, Flack Labbers, let's ask a question. A big one. What if the moon was made of cheese? Not just any cheese. Imagine a colossal, cratered sphere of sharp cheddar orbiting our planet. It sounds like a joke, something from a children's cartoon. And it is a funny thought. But sometimes the silliest questions lead to profound scientific truths. By imagining a dairy-based satellite, we can peel back the layers of cosmic mechanics and see why our rocky moon is so important to life on Earth. So, come on, let's take this delicious premise for a spin. It's a thought experiment, a journey of cosmic curiosity. Our universe is governed by laws: physics, motion, gravity. Before we can replace our moon with a dairy substitute, we need to appreciate the one we already have. The real moon is not just a pretty light in the sky. It is a critical component of the Earth-Moon system, a cosmic partner in a gravitational waltz that has been going on for billions of years. It's a colossal sphere of rock and metal, a silent guardian that profoundly influences our world from 250,000 miles away. Its most obvious effect is its gravitational pull, the force that dictates the rhythm of our planet's oceans. This pull is what creates the tides, the twice-daily rise and fall of sea level that shapes our coastlines and drives life in tidal ecosystems. Let's get specific with some numbers, because the universe runs on numbers. Our moon has a mass of approximately 7.342 times 10 to the 22nd power kilograms. That's a 7 followed by 22 zeros. It's an immense amount of stuff. Now for the fun part. Let's perform the cosmic swap. We take our dense, rocky moon, replace it with an identical size sphere made of cheddar cheese. To understand the consequences, we need only middle school math. The key is density. Moon density, 3.34 grams per cubic centimeter. Cheddar density, 0.93 grams per cubic centimeter. Cheese is less dense than water. It would float. Rock, on the other hand, sinks. If the volume stays the same, mass scales with density. Set up the ratio. New mass equals old mass times new density over old density. Do the division. 0.93 divided by 3.34. The result is approximately 0.28. So the cheddar moon would have about 28% of the mass. Let that sink in. We've shed nearly 3/4 of the moon's mass. It's the same size in the sky, but its gravitational influence is drastically reduced. With our cheddar moon weighing in at a mere 28% of the original, the most immediate and noticeable effect on Earth would be the quietening of our oceans. The tides are a direct result of the moon's gravitational caress, pulling a bulge of water toward it as it orbits. With a much weaker pull, these tidal bulges would shrink dramatically. High tides would be much lower. Low tides would be much higher. The intertidal zone, that vibrant strip of coastline, would be drastically reduced. For surfers, this would be a tragedy, but the consequences go far beyond recreation. The mixing of ocean water driven by tides is a vital planetary process. It's like a giant circulatory system, pulling nutrient-rich cold water up from the depths and circulating oxygen down to the abyss. This process, known as tidal mixing, is the foundation for many marine food webs. Plankton and other microorganisms at the surface rely on these nutrients. With significantly weaker tides, this oceanic conveyor belt would slow down. The surface waters could become nutrient-poor, potentially leading to a collapse in phytoplankton populations, which would have devastating ripple effects all the way up the food chain, impacting everything from small fish to great whales. Let's consider the aesthetics of our new celestial neighbor. The moon shines not with its own light, but by reflecting the light of the sun. The rocky, dusty surface of our current moon, regolith, has a specific reflectivity, or albedo. It's actually quite dark, reflecting only about 12% of sunlight. About the same as worn asphalt. Now, imagine a cheddar moon. A fresh block of cheddar is a pale, creamy yellow. Its albedo would be much higher than lunar rock. A cheddar moon would reflect far more sunlight, appearing significantly brighter in our night sky. A full cheddar moon could be dazzling, casting sharp shadows, washing out all but the brightest stars. However, this bright facade hides a soft, vulnerable core. Space is not an empty, peaceful void. It's a shooting gallery, micrometeoroids, asteroids, comets. Our moon's craggy face is a record of billions of years of cosmic bombardment. It has acted as a shield for Earth, absorbing impacts that might have otherwise been catastrophic. A cheddar moon would fare very differently in this hostile environment. All this cosmic speculation is fascinating, but science is also about doing. You don't need a billion-dollar laboratory to explore these principles. You can create a simple model right in your own kitchen to visualize the difference between a rock moon and a cheese moon. This experiment won't perfectly replicate gravity, but it will give a tangible, hands-on demonstration of density and mass and their effects. It's a fun way to bring a cosmic concept down to Earth. So grab household items. Let's get experimenting. Here's what you'll need for your home model. First, a large, shallow tub or basin filled with a few inches of water. This will represent our ocean. Second, find a large ball to represent the Earth. Visual option. Basketball. Visual option. Small beach ball. Third, you'll need your two moons. For the cheddar moon, a round piece of cheddar. Or more simply, a small, light foam ball as the cheddar moon alternative. For our real, rocky moon, use another ball the same size but much heavier. Option, a billiard ball. Option, a large marble. Option, a dense rubber ball. Now let's run the experiment step by step. First, take your rocky moon, the heavy ball. Hold it close to the side of your earth ball, just above the surface of the water. Now, slowly orbit it around the tub. Watch the water closely. You should see the water being pulled slightly toward the heavy ball, creating a tiny tidal bulge that follows it as it moves. That mimics the gravitational pull of our real, massive moon on the oceans. Next, remove the rocky moon. Repeat the exact same procedure with the cheddar moon, the light foam ball. Hold it at the same height and move it at the same speed around your water-filled basin. Observe the water's surface. What do you see? Most likely, you will see very little movement at all. The light foam ball has insufficient mass to exert a noticeable pull on the water. This is a direct visual representation of what would happen with a cheddar moon. Its lower mass translates to a weaker gravitational pull, resulting in diminished tides. This simple comparison powerfully illustrates our core concept. For the same size, greater density means greater mass, and greater mass means a greater gravitational effect. Our thought experiment has focused on cheddar, a solid, reliable cheese, but the world of cheese is vast and varied. What if the moon were made of a different kind? The properties of the cheese would dictate a whole new set of cosmic consequences. Imagine a moon made of brie. This soft, creamy cheese has a much lower melting point and structural integrity. The sun's heat would turn the lunar surface into a gooey, molten blob. Any craters would quickly fill in with flowing, melted brie, and the entire moon might struggle to even hold its spherical shape, perhaps deforming into a wobbly, unstable mass. Landing a spacecraft there would be like trying to land on a planet-sized pot of pudding. Now, let's consider a Swiss cheese moon. The iconic holes, or eyes, in Swiss cheese are formed by gas bubbles. A moon-sized sphere of Swiss would mean its mass is not evenly distributed. It would have vast empty pockets within it. This uneven mass distribution would cause the moon to wobble in its own orbit, and its gravitational pull on Earth would be irregular. As it rotated, the tides would fluctuate unpredictably, depending on which part of the moon, a dense part or a holy part, was facing Earth. How about a hard-aged cheese like Parmesan? Parmesan is brittle and crumbly. A Parmesan moon would be much more resilient to melting than brie, but far more susceptible to shattering upon impact. Every meteor strike would send up a massive plume of dusty, grated Parmesan. As we discussed earlier, This debris could easily form a dense ring system around the Earth, potentially becoming a permanent fixture of our sky. Our planet would look more like Saturn, encircled by a ring of savory, aged cheese particles. This would create a navigational nightmare for satellites and could even slightly dim the sunlight reaching Earth. Finally, let's get weird and imagine a blue cheese moon, streaked with veins of mold. From a scientific standpoint, this introduces the fascinating idea of extraterrestrial life, albeit in a very strange form. Could the mold, a living organism, survive the harsh radiation and vacuum of space? Probably not, but it forces us to think about planetary protection and contamination. If we were to visit, we'd have to consider whether we were bringing Earth microbes to the cheese, or, even more bizarrely, whether any space-hardy mold spores could potentially survive a journey back to Earth. This galactic deli of cheesy moons shows us that even within our silly premise, the specific details matter immensely. Now I challenge you. Pick your own cheese, do the math, and tell me in the comments what kind of wild, delicious fate Earth would face. Stay curious. These rules don't care if an object is silicate rock or aged Gouda. Mass, density, distance. The real moon is a massive ball of rock. Its presence is woven into Earth's daily rhythms. It dictates the ebb and flow of our oceans. It stabilizes our world on its axis. Swap rock for cheese and the gravitational dance changes. Let's get our hands a little greasy and explore the science. This isn't just abstract numbers or distant bodies. It's about connecting the cosmic to the common. We all know what cheese is. Hold it, weigh it, taste it. That familiarity gives us an intuitive entry point into complex ideas. Lunar regolith density sounds academic. Compare it to cheddar, and suddenly it's relatable. A good thought experiment brings the cosmos to your kitchen counter.